Sorry, we got cut off there. So nonmetals are going to be basically the opposite of metals. So instead of losing an electron, they're going to gain an electron. So they're going to become positive when they become ions. They have a high ionization energy. They're really crappy at being a conductor of heat and electricity. They're brittle and hard, so they can snap easily. They have low densities, but with this one, the most active nonmetal is going to be fluorine, which is going to be in the top right. So for metals, it was bottom left. Nonmetals, top right. Metalloids is going to be this like awkward little group in the center. So like this is where metals cut off. Metalloids, which is going to be a mixture of metals and nonmetals, kind of creates this like little staircase here. Ooh, I did a little overlap, my bad. Okay, so these blue ones are going to be your metalloids. So depending on the element, they can either gain or lose an electron when they're forming bonds. They have properties that are similar to both metals and nonmetals, so it really depends on the element that you're looking at. And they're kind of create this weird little staircase. Boron, silicon, germanium, arsenic, antimony, and beryllium are going to be your metalloids. Okay, let's talk periodic bond trends. Or I guess this one is more covalent. Let's talk atomic radius, is basically. So if we have an atom, okay, so it has 7 neutrons, 7 protons. This is the center of our atom. 7 protons, it's going to have 7 electrons. So we'll have in that first shell 2, and then in that next shell we'll have 5. 2, 3, 4, 5.
We'll be right back.
Okay. Okay. Sorry. Okay. So this is our atom. Okay. Your atomic radius is going to be from the center of the atom to that outer shell. Okay. Center of the atom to the outer shell. So depending on the atom, it's going to have a larger atomic radius or a smaller one. So if you look at your periodic table, your valence electrons aren't really going to help you. So I think there's a question in your packet. It's basically asking, why can you check the atomic radius on Bohr's head but not the Lewis structure? Bohr's head is going to give you this full diagram. You'll be able to see every energy level of this atom. But nitrogen, if we were to do the Lewis structure, you're only looking at the valence electrons. If you look at your periodic table, here I have another one. This is 1, 2, 3, 4, 5. So this is group 5. So it's only going to have 5 valence electrons. So this is what the dot structure is going to look like. Nitrogen and arsenic have the same number of valence electrons. So their Lewis structure is going to look very similar. But their Bohr's model is going to look very different because arsenic has a lot more electrons. So while this is where nitrogen stops, arsenic is going to keep going until you have a complete model. So that's why Bohr's head works for atomic structure and Lewis structure does not. So let's look at our periodic table. As you move across the table, so as you go left to right to the period, your radius is going to get smaller. Okay, so your radius is going to get smaller, but your energy levels are going to be the same. As you move up and down the group, your atomic radius is going to increase, so it's going to get larger. And that's because your energy levels are getting larger as well. So there's a diagram in the notes that's going to be really helpful just to give you a better idea of it. Okay, so ionic radius is basically when you lose or gain an electron. This is obviously going to cause your atom to change. So if you have a positive ion, so you lost an electron, your size of your atom is going to change because you're losing a piece of it. So metals are going to lose electrons when they form ions, while when metals lose their electrons, they're losing something, so everything is moving closer together. So like sodium, a sodium atom is going to be larger than a sodium ion. But for nonmetals, it's going to be the opposite. Nonmetals are going to gain an electron, so they're adding something to their atom. So when they form the anion, their radius is going to get bigger. So chlorine is going to be smaller than a chlorine ion. Ionization energy is going to just be the amount of energy needed to remove the most, like a valence electron, okay? So as you move across your table, energy is going to increase. So as you go from like sodium to phosphorus, your ionization is going to increase. And that makes sense because you have more valence electrons. So you're going to need more energies to remove them. As you go up and down, it stays the same. But it's getting larger. So lithium has 1 valence electron, so does francium. But lithium has a much smaller atom where it's able to keep everything closer together, while francium is pretty big. So that 1 electron all the way at the last ring of this atom that has 87 protons is going to be, it's just going to be a quick getaway. Electronegativity is going to be how attracted the electrons are when they're bonded to each other. So as you move from left to right, your electronegativity is going to increase. As you move down, it's going to decrease in the group. Okay? And as you move across, your valence electrons, so like rubidium has 1 valence electrons. It's not super attracted to other electrons just because it's just kind of there. But if you go to that halogen, so like iodine, this one is so close to having its outer shell filled that it just wants to do it no matter what. So it's kind of, think of it as like a road trip. If you're 5 hours away from your destination, you don't mind stopping and going to the bathroom and stretching. But if you're 45 minutes away on a long road trip, you kind of just want to get there and be done with it. Okay? So then we have groups within the groups. So our first group is going to be the alkali metals, and that's going to be all of these. So all of these have very similar properties to one another. Okay? So, ooh, I'm sorry, I should have not included hydrogen. We're just going to erase that one. That's not working. Don't include this one. Hydrogen is its own group. The only thing it shares with group 1 and the alkali metals is the valence electrons. Group 2, the second one, all of these are included. These are going to be the alkaline earth metals. So these all have 2 valence electrons. They're going to have a charge of 2 when they bond, but we haven't gotten to bonding yet, so you don't need to know that for your test. Okay. Next is going to be the transition metals. So it's kind of these like awkward in-between ones. So if you remember from valence electrons, or what is it from, yeah, just from electrons in general, this was like the D block and the F block. These are kind of like on their own ball game. You just need to be able to identify them. Not so much worried about like any properties that they have. These are still going to be metals, so they'll have those characteristics. So these are going to be less reactive than these 2 groups because they're just kind of chilling, but they are going to form more ions. Then we're going to go to our halogens. So these are this group over here. These are ready to be noble gases. Like they're 1 atom or 1 electron away from it. They're ready. They have 7 valence electrons, and when they become ions, they always have a -1 charge. Last but certainly not least is going to be our, let's pick a color, is going to be our noble gases. These are like where it's at. These are the ones that are kind of just chilling. They're living their best lives. They're good. They have all their energy levels full. They don't feel the need to combine with other elements because they're perfectly content with, sorry, my stand. They're perfectly content with what they've got. They're stable, and basically the other elements want to be like them. Okay, that's going to be all for this video. Please let me know if you need anything. Sorry for all the interruptions.